3.3 Problem solving with combinations. So now we're going to combine the rule of sum and fundamental counting principle with combinations so that we can solve some counting problems. So let's recall a few things. So with sets, we said that the order doesn't matter. So ABC is still the same as CAB. Okay, order doesn't matter. Furthermore, we learned that the number of subsets of a set with n elements is given by this little formula here called 2 to the exponent n, where we said n equals the number of items, and the 2 here refers to the number of choices for each item. So the number of choices for each item. Okay. And also in combination, since order also doesn't matter, we can use properties of sets along with the rule of sum and the fundamental counting principle to solve some problems. Okay, so let's look at an example of such a problem. So example 1, suppose you stop for a snack at the corner store. You can't decide if you want a bag of popcorn, chips, or licorice. In how many ways can you choose one or more items for your snack? Let's list the possibilities. So we could have either popcorn or chips or licorice or popcorn and chips or popcorn and licorice or chips and licorice or all three, popcorn, chips, and licorice. So how many possibilities are there of one or more items for our snack? Well, we have 1, 2, 3, 4, 5, 6, and 7. So we have a total of 7 possibilities. Okay, so since the snack includes at least one item, mathematically the total number of combinations can be found by using a couple of methods. So here, method 1, using combinations and the rule of sum. So the sum of the possibility of choosing one item or two items or all three items. So we could have done 3 choose 1, so choosing one of those items from a set of 3. So I'm just going to write here, so this arrow, choosing just one item. Then we could have added that to the number of choices, so 3 choosing 2 items. So choosing 2 of the 3 items. And then we could add that to the combination of 3 choose 3, so choosing all 3 items. Okay, and so that will leave us with 3 plus 3 plus 1, which is equal to 7 total possibilities. Okay. The second method would be using sets and the indirect method. So the total number of possible snacks minus the possibility of selecting no snacks. So total number of possible snacks. So here 2 to the exponent n, which is 3, and this refers to 3 items that you can take or not take. Okay, minus 1. So we're going to subtract the 1 of not choosing anything. So this is the one case. So the one case of not choosing anything. And that leaves us with an answer of 8 minus 7, which is equal to, 8 minus 1, which is equal to 7. Same answer. Okay. So the total number of combinations containing at least one item chosen for a group of n distinct items is given by this following formula. A set with n distinct elements has 2 to the exponent n subsets, including a null set, a set that has no elements. Example number 2. In how many ways can the committee with at least one member be appointed from a board with 12 members? So to use a direct method would look something like this. So you would say direct method. Now you can choose, if it's at least one member, you're looking at, okay, 12 people choose one, plus 12 people choosing two members for our committee, plus 12 choosing 3 members for our committee, plus 12 choose 4, etc., 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 until you reach 12 choose 12. And this could be kind of time consuming. So I'm going to say here this is time consuming. So what's another way that we could possibly do it? Well, let's look at an indirect method. Indirect method says, well, if I have 12 items or 12 members, so I have 2 to the exponent 12, and I'm going to subtract 1, and that 1 represents the one case where we have no board members, okay? And that's going to give me a number of combinations of 4,095. So 4,095 ways to select a committee with at least one member. Okay. Moving on, example number 3. So here's an example of combinations with some identical items. Okay. So Ravi needs to stock the office coffee room with snacks. He can purchase up to 3 cases of cookies, 4 cases of juice, and 2 cases of coffee without having to send the order through the accounting department. How many different purchases can he make? Okay, so let's look at cookies. 3 cases of cookies. So he can buy, let's see what he can buy. So he can buy um, either 3 cookies, 2 cookies, 1 cookies, 1 cookie, or none. Okay, so 0 cases. So how many possibilities is that? Well, let's count them up. 4 possibilities. Then we look at, well, let's read this question carefully. Up to 3 cases of cookies, 4 cases of juice, and 2 cases of coffee without having to send the order through accounting. How many different purchases can you make? So you got to be very careful here. So I'm going to look at combining them using and. So cookies and juice and coffee. Okay, it's not an or problem, it's an and problem. Okay, so we're looking at the different ways that we can get juice. If we have 4 cases of juice, we can have 4, or we can buy 3, we can buy 2, we can buy 1, or we could buy none. Okay, the null set, 0 cases. So 0 cases. And that means we have 5 possibilities for buying juice. And then if we finally go with the number of cases of coffee, well, we can have either 2 cases of coffee, 1 case of coffee, or no cases of coffee, which means we have 3 possibilities. Okay, so we must choose at least one combination. So the way we're going to do this is the multiplicative counting principle. Just take 4 times 5 times 3, and we subtract 1, because that 1 represents the case where we buy nothing. Okay, but we do need to, but we are interested more on only the possible combinations where we actually purchase something. Okay. So that gives me a total of 59 possible purchases. Okay. So if you have to choose all, some, or none of P available items, you have p plus 1 available choices. Okay, so using all the fundamental counting principle, if you have successive choices of different kinds of items, then the total number of combinations that can be made from p items of one kind, q items of another kind, r items of a third kind, etc., is p plus 1 times q plus 1 times r plus 1. Don't forget to think whether or not picking any items makes sense. If at least one item is chosen, then the total number of selections is p plus 1, q plus 1, times r plus 1 minus 1. Okay? Example number 4, combinations with some identical items. So here we have a question here. So let's read this question. The director of a short film has found 5 rock songs, 2 blues tunes, and 3 jazz pieces for his film. In how many ways can he choose 3 songs for the soundtrack if the film must include some jazz? So we're going to have some combinations with one jazz piece. So what are those combinations? Well, we have so that's 5 rock songs, 2 blues, and 3 jazz. So we can have 3 choose 1 because we have to have one jazz piece times 7 choose 2. So we're going to choose. We have 7 choices for the other 2 songs, 5 from 5 rock and 2 blues. So that gives us 3 times 21, which is 63. Okay, or we could have uh, 2 jazz pieces. So that means we have 3 choose 2. So 3 jazz pieces, we're going to choose 2 of them, multiplied by the 7 remaining songs, but we're going to choose 1 to round out our choice of 3 songs. So that gives me 3 times 7, which is 21. Or we can choose 3 jazz pieces. So we have 3 choose 3 times 7 choose 0, which is 1 times 1, and that's equal to 1. So therefore, having 1 or 2 or 3 jazz pieces, what we got to do is add up the different combinations. So 63 plus 21 plus 1, which is 85 ways to select some jazz. Okay. When using cases to determine the number of ways to select objects from different sets, find the number of occurrences for each set and then use the rule of sum since the events are mutually exclusive. Okay, remember, so these are mutually exclusive events. So if I want to use an indirect method, I'm going to just show you how here. So indirect method. Any 3 songs. Cases with no minus cases with no jazz equals the number of combinations of having some jazz. Okay, so any 3 songs. Well, 10 songs, choose 3 of them. We subtract the cases with no jazz, so these are the other 7 songs. We chose 3 of them, and that will equal 120 minus 35, which is 85. Okay, so this is the 10 songs. We're choosing 3 of them. Subtract the other 7 songs. The other 7 songs are the 5 rock and the 2 blues. So those 5 rocks and 2 blues, choosing 3 of those instead of any jazz will give me this result. So 85 ways to select some jazz. Same way, same answer as the direct method. Okay, more counting cases. So example number 5. The card game Euchre uses only 24 cards. The 9s, 10s, jacks, queens, kings, and aces of each suit. 5 card hands are dealt to the players. How many Euchre hands contain 2 kings? Okay, so let's just write that here in the top. That in the game of Euchre, we have 12 red cards, and we have 12 black cards. and 6 of each suit. Okay. Um, so remember 9, 10, Jack, Queen, King. So and the Ace. So that's 6 cards. So 6 plus 6 is 12 red, and another 6 plus 6 is 12 black. That's what I'm saying. So 6 of each suit. That's how I'm getting these numbers here. 24 cards. Okay. So how many euchre hands would contain 2 kings? Well, how many kings are there? Well, there are 4 kings, right? So 4 choose 2 times 20 choose 3. So these are there are 20 cards that are not kings, and I have to choose 3 more to round out the hand of 5. Right. So this refers to the cards without kings. Okay. So that equals 6,840 possible hands. All right, 2 or 3 hearts. Well, then I'm interested in now having 6 choose 2, okay, because there's 6 hearts to choose from, times 18 choose 3 for the rest of my hand, plus the number of combinations of choosing 3 hearts. So 6 choose 3 times 18 choose 2. Now remember, I'm separating them by a plus sign because this is an OR problem. Okay. So that gives me 15 times 816 plus 20 times 153, and that's 15,300 possibilities. Okay. What about at least 2 hearts? So, okay, at least 2 hearts. Let's figure it out this way. So we can have any 5 cards minus 5 cards with no hearts, minus 5 cards with 1 heart. Okay, so at least 2 hearts. So any 5 cards. That's I'm looking for all the combinations of just having any 5 cards. I subtract the combinations of 5 cards with no hearts, and I subtract the combinations with 5 cards with 1 heart. And that will give me what's left over would be at least 2 hearts. Okay, so there are 24 cards, choosing 5 of them, minus 18, choose 5. Okay, because there are 6 cards with no with no with no hearts, and then uh, sorry, there's 6 cards with hearts, so there are 18 cards with no hearts, I should say. I said that incorrectly. And then 5 cards with 1 heart. So I'm going to do minus 6, choose 1, times 18, choose 4. Okay, remember independent events, you have to multiply them. So I have to have 1 heart, so 6 choose 1, and then the other 4 cards are not hearts, so 18 choose 4. Okay, and then finding all these combinations here, I will have a number 42,504 minus 8,568 minus 18,360, which is equal to 15,576 possible hands. Yeah, yeah, possible hands. Okay, what about a flush? So all 5 cards being the same suit, that's what we call a flush. So we can either have 5 hearts, or 5 clubs, or 5 diamonds, or 5 spades. So remember, or problems, we're going to be adding these combinations. So 6 hearts, choosing 5 of them, plus 6 hearts, choosing 6 clubs, choosing 5 of them, plus 6 diamonds, choosing 5 of them, plus 6 spades and choosing 5 of them. Okay. Add up all these combinations. We get 4 times 6, choose 5, and simplifying that is 4 times 6, which is equal to 24 possible hands. There are 24 ways to get a flush. Okay, what about 2 aces or 3 clubs? Well, that one's also not too bad. So 2 aces or 3 clubs. Well, there are how many aces? So there are 4 aces. I want to choose 2 times 20. Choose the other 3 cards in our hand. So there are 20 cards left out of the 24, which are not aces, and those will make up the other 3 cards in the hand. So again, independent events, multiply the 2 combinations. Plus 6, choose 3, times 18, choose 2 for the 3 clubs. So this part here represents my 2 aces. This part here represents my 3 clubs. Okay, but I'm going to have another term here. So I'm going to have 1, choose 1, times 3, choose 1, 3, choose 1, times 5, choose 2, times 15, choose 1. Now let me explain what's going on here. So this whole thing represents the ace of clubs with one other excuse me, one other ace and 2 more clubs plus 1 non-ace, non-club card. Okay, what does that all mean? Well, because these events are non mutually exclusive, okay, I have to subtract the intersection because of 2. You said it says here 2 aces or 3 clubs. Okay, the thing is, these 2 sets, the sets of these events where we have aces and clubs, they intersect because you can have an ace of clubs. So that's going to be double counted again. Okay, so you have to subtract the possible hands where you can get an ace of clubs with one other ace. Okay, so there are two aces, so one other ace, and 2 more clubs plus 1 more non-ace, non-club card. Okay, so 1 choose 1 represents that ace of clubs times 3 choose 1, which is the other 3 aces. Okay, so you're choosing one other ace. 5 choose 2, and then 15 choose 1. So 5 choose 2 representing the possible clubs times 15 choose 1, which is the other non-club and non-ace card. 15 being non-club, non-ace. Okay, so that's my entire mutually exclusive formula, rule of sum, and that will give me an answer of 60 times 6 times 1, 1540, plus 20 times 153 minus 450, which equals to 11,850 possible hands. And then finally, example number 6. So Ming has 8 pictures of family and 5 pictures of friends. Her wall shelf will only hold 5 pictures. Ming decides she wants to use 3 family and 2 friend pictures. In how many ways can Ming arrange the pictures on the shelf? Well, first to select the photos. So there are 8 pictures. We're going to choose 3 of them times 5, choose 2. So for the friends. So 8 pictures of family and 5 pictures of friends. We can only hold 5 pictures, so 3 of them are family and then 2 are friends. Okay, and this is going to give me 56 times 10, which is 560 possible selections. Okay, and then we're going to arrange the photos on the shelf. So then arrange photos on the shelf, which is not a combination problem. This is a factorial problem. 5 factorial, 5 picture frames. So it's going to be 5 factorial ways to arrange them. So 120 arrangements. So therefore, multiplicative counting, if we have 560 possible selections for the photos times 120 ways to arrange the picture frames, that will give us 67,200 possible selections and arrangements and combinations. 67,200 possible selection uh, slash arrangement combinations. So this is an example of a type of problem where we combine combinations with permutations.